112 gigabits per second and for transmission over 50 kilometers SMF using absolute term-based nonlinear Ffe-Dfe. Here's the outline. I will start with the introduction. According to Cisco Visual Networking Index forecast in 2018, global IP traffic will grow rapidly from the 2017 to 2022, especially in the inter-data centers and the inter-data centers and other short-haul and intermediate haul optical interconnections within 100 kilometers. Massive growth in these optical links enables system operating at 100 gigabits per second data rate and beyond in a cost-effective manner. Hence, intensity modulation and direct detection IMDD scheme is favored due to its small form size, low cost, and low power consumption. Especially the PAM4 is a promising modulation format applied in high-speed IMDD system for the next generation 800G Ethernet. However, the existing chromatic dispersion CD in the standard single-mode fiber SSMF induces the different frequency components of signal propagate with a different phase response and causes the frequency power fading after square detection, especially in the high-speed IMDD system at C-band. Here's a figure showing the optical response after square detection versus the frequency on different transmission distances. Due to the CD-induced frequency power fading, different frequency dips can be observed on the different frequency, different distances. Longer distance, more dips will appear. And around these frequency dips, the frequency components of signal have bad SNR or even cannot be detected. To compensate that, different algorithms have been proposed, such as the feed-forward equalizer FFE and the decision feedback equalizer DFE and the Tomlinson-Harrison recoding THB and so on. Among these algorithms, the combination of FFE and the DFE is preferable, since the FFE is robust and the DFE with the structure of infinite impulse response can successfully equalize the frequency dips. Besides, there also are nonlinear distortions, including from the intensity modulation and electrical amplification in the transmitter, and from the fiber channel and from the square law detection in the receiver. The nonlinear compensation is better to cope with the nonlinear distortions and the CD-induced frequency power fading simultaneously. The Volterra and the polynomial-based nonlinear FFE and DFE are the most representative solutions. But the V and the P and FFE-DFE both pose high computational complexity at the increase of the memory length and the order of nonlinearities, which causes the burden to the system's implementation complexity. Compared to the V and FFE-DFE, the P and FFE-DFE with only the main diagonal of V and FFE-DFE reduces the complexity. Here's a strat of P and FFE-DFE. The different order input terms, FFE part and the DFE part with the decision block and the different order decision terms. As the equation shows here, the final equalized output Y is the sum of FFE filter convolutes the different order input terms, and DFE filter W convolutes the different order decision terms. However, the P and FFE-DFE still poses a high complexity to the cost-effective IMDD systems. So in this paper, we reduced the complexity of the second order P and FFE-DFE by replacing its square terms of FFE and the DFE with the corresponding absolute terms, and we call it the second order absolute term based AT and FFE-DFE. Obviously, the AT and FFE-DFE can reduce the required number of real-valued multiplications to reduce the complexity. Specifically, with the same memory length, the linear memory length N1 and D1, and the nonlinear memory length N2 and D2, the P and Ffe-Dfe has the RNIM of N1 plus 2N2 plus D1 and plus 2D2, while the proposed AT and Ffe-Dfe has only the RNIM of of N1 plus N2 plus D1 plus D2. In the following slides, I will also show the good performance of the proposed ATNFV applied in the high-speed IMD system, up to 112 gigabits per second over 50 kilometers transmission. Here's the experimental setup. In the transmitter, 56 kilobaud PAM4 generated from the arbitrary waveform generator operating at 120 gigasamples per second is modulated to the light at the wavelength of 1550.12 nanometer from the external cavity laser via the commercial tube-free multi-center modulator, MZM. This MZM has 3 dB bandwidth around 32 gigahertz. After 50 kilometers SMF transmission, the optical signal is attenuated by a variable optical attenuator to alter the received optical power, ROP, and followed by an adopted fiber amplifier to keep the constant power injected into the photodetector. And the detected electrical waveform is collected by the 256 gigasamples per second oscilloscope. As for the Dsp procedures, they include the resampling to 2 samples per symbol and the synchronization and the different equalization schemes of AT and the P and Ffe-Dfe and the conventional Ffe-Dfe. All these algorithms are trained using the recursive least square estimation, and finally goes to the VR calculation. In the pursuit of the optimal parameters, we first optimize the linear memory length N1 and D1 at the ROP of -11 dBm. All results are shown in this figure on the different value of D1 marked in different color. All BRs get better with the larger N1, and the lowest BR can be achieved when N1 equals to 100 and the D1 equals to 34. And values exceed these two, the BR performance saturates. And obviously, even this the best BR cannot reach the 7% hard decision FEC BR threshold of 3.8 times 10 to the -3rd. Next, we optimize the nonlinear memory length N2 and D2 with the fixed N1 to 100 and the D1 to 34. All results are shown in these two figures, respectively, for the P and AT and Ffe-Dfe. And the best BRs for both two algorithms are achieved under the same nonlinear memory length, N2 96 and D2 22. And then we calculate the corresponding RNIMs for both the two algorithms. For P, it has 370 RNIM, and for AT and Ffe-Dfe, it has 252 RNIM. Obviously, the AT and Ffe-Dfe has much lower RNIM, and it saves about 31.9% RNIM compared to the P and Ffe-Dfe. And we also measure the BR versus the RNIM by varying the N2 and the D2, also with the fixed N1 to 100 and the D1 to 34. When achieving the same BR performance, the AT and Ffe-Dfe this area are much better than has much lower RNIM compared to the P and Ffe-Dfe. The results are shown in this area. And both for the two algorithms, the lowest RNIM are achieved under the BR threshold, respectively 214 RNIM and the 286 RNIM. And even this, the AT and Ffe-Dfe still saves about 25.2% RNIM compared to P and Ffe-Dfe. And also they need the nonlinear memory length D2 both 0 and N2 are 80 for the AT and Ffe-Dfe and the 76 for the P and Ffe-Dfe. Finally, we tested the BR performance versus the ROP for both three algorithms. and under the same parameters, same optimal parameters, and 100 and D132, 34, and D296 and D296 and D222. And as mentioned before, that only using the Ffe-Dfe cannot make the BR reach the FEC limit. And with and among these three algorithms, the BNF-Ffe-Dfe still always achieve the best BR performance. And but with the extra RNI compared to the ATN Ffe-Dfe, but the penalty between the ATN Ffe and the PNF Ffe-Dfe is marginal. Under the FEC limit, the penalty is less than 0.5 dB. So as a trade-off, considering all of these, the proposed ATN Ffe-Dfe is still promising, applied in the cost-effective high-speed IMD systems. And there are 4 diagrams are shown here. Compared to the Ffe-Dfe without the nonlinear compensation, the I diagrams are not so clear. But with the PNF Ffe-Dfe and ATN Ffe-Dfe with the nonlinear compensation, the I diagrams are much clearer. And finally, it goes to the conclusion. In this paper, we propose a low complexity absolute term-based nonlinear Ffe-Dfe and apply it to a 112 gigabits per second PAM4 MDD system of 50 kilometer standard single fiber transmission. And this proposed ATN Ffe-Dfe has much lower RNI compared to the PNF Ffe-Dfe. It serves about 25% and 32% RNI at the BR of 3.8 times 10 to the negative third, and add the optimal BR with the less than 0.5 dB power penalty, respectively. All these results highlight the potential of the proposed ATN Ffe-Dfe implemented in the high-speed IMDD systems at the C-band beyond the 50 kilometer transmission. And that's all for my presentation. Thanks for your attention.
Hi, Wushong, are you online?
Yes, I'm here.
Okay, so now because of the limited time,